Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good morning to our rector of UiTM Cawangan Terengganu, Professor Dr. Mazidah Putih, Timbalan Rector Academic Associate Professor TS Dr. Sharifah Fauziah Said Draman, Timbalan Rector Hal Ehwal Pelajar Dr. TS Dr. Elmi Abdul Kadir, and to all distinguished participants and students. On behalf of the third Terengganu Multidisciplinary International Conference 2023, which known as TeMIC 2023, I welcome you all to the keynote address of the fourth International Conference of Emerging Challenges in Engineering and Current Technology organized by UiTM Cawangan Terengganu. And we are honored here because we have our distinguished keynote speaker. Okay, I am excited to introduce our keynote speaker from the University of Auckland. Okay, let me introduce our speaker today, Dr. Duleepa J. Thrimawithana. I hope I get your name right. Okay, received his BE in Electrical Engineering with first class honors in 2005 and his PhD in Power Electronics in 2009 from the University of Auckland, New Zealand. And we also have our alumni here, Dr. Elmi, University of Auckland. Okay. From 2005 to 2008, he worked in collaboration with TM Test Limited in Auckland as a research engineer in the areas of power converters and high voltage pulse generator design. He joined the Department of Electrical and Computer Engineering at the University of Auckland in 2009, where he currently works as a senior lecturer. He has co-authored over 100 international journal and conference publications and holds 24 patent families on wireless power transfer technologies. And in recognition of his outstanding contribution to engineering as an early career researcher, Dr. Thrimawithana received the Jim and Hazel D. Lott Fellowship in 2014. His main research areas include wireless power transfer, power electronics, and renewable energy. We actually are truly fortunate to have such accomplished and influential personality with us today, ready to share his wisdom and insight on engineering, innovation, and energy sector. So without further ado, let us give a warm welcome to our keynote speaker, Dr. Duleepa J. Thrimawithana. The floor is yours.
Got it? Cool. All right. Good morning, distinguished guest and all the participants. Thank you for having me. Thank you very much for having me in Malaysia. It's quite nice. So my name is Duleepa, and I'm from the University of Auckland in New Zealand. And today in our presentation, I thought I'll share a little bit about what we do at the University of Auckland around wireless power transfer, especially with the target of reducing carbon emissions and how we can apply that in the reduction of carbon emissions. So before I go into the technical details, I thought maybe I'll give a little bit of an introduction to the University of Auckland and my department and my research group. And then we'll talk a little bit about the history of wireless power transfer. And then finally, we'll go down into a little bit more of technical stuff, things like how does a wireless power transfer system work? Finally, I'll end the presentation with a little bit of work we do at the University of Auckland. Okay. Right, so here is a map of Auckland City. It's a very nice place. You can see aerially we are surrounded by the sea, like you got the sea around here as well. And the University of Auckland is located right in the middle of the city center. You can see 3 blocks because we had 3 main campuses. The one right in the sort of I can't use the mouse pointer, but right in the closer to the sea is the main campus, the city campus. It's right in the middle of the city, and that's where almost all of the teaching happens. Then the middle block is our medical campus, where the hospital, the medical degrees, like the pharmaceuticals, the optometry, and the Bachelor of Medicine is taught. And then the one right at the end, the smaller block, is what we call the innovation precinct. That's where we work with industry, taking some of the new ideas that we develop in the university into the industry and to the commercialization side of things. So University of Auckland, we are fortunate, we are very well ranked out of the top universities. We are considered one of the top universities globally. This year ranked at 68th. And we got about 40,000 students, about 5,000 staff members. So it's a very large organization. In the university, we got a number of faculties. And engineering faculty is where I come from. In the engineering faculty, we got many. So you got the engineering faculty, and then you got departments within the engineering faculty. We got 5 of them. And electrical, computer, and software engineering is my department. And the other departments are like mechanical engineering, civil engineering, engineering science, and so on. So I come from Faculty of Engineering, Department of Electrical, Computer, and Software Engineering. Like the name suggests, our department teaches 3 degree programs: Electrical and Electronics Engineering, Computer Systems Engineering, and Software Engineering. So in the department, we got about 700 students across the 3 years of the degree program. And we got about 35 staff members who's teaching these students. And we pride ourselves as a university that teaches undergraduate degrees mainly based around project-based courses. So a lot of courses we teach, they're hands-on project-based activity, where you're actually working on projects together with the industry to learn the latest industry practices. So that's our new engineering building. So you see the first photo, that's the front-facing part of our engineering faculty. And behind this, we have a new building which was opened 3 years ago, just when COVID started in 2019. So it's still brand new because we hardly used it. I am on level 6 of that building, where we have our research labs, and then we have all our undergraduate teaching labs. Everything's brand new, huge facilities with state-of-the-art equipment. So within the electrical, computer, and software engineering department, we got many research groups. Among those research groups, I come from the Power Electronics Research Group, which is regarded as one of the top power electronic research groups globally. And that's because some of the outstanding work we have done over the many years. We've been established in the 80s by a professor called Professor John Boyce. So it's 80s to now, 2023, almost 40 years of experience in the sector of power electronics. And throughout the years, we have developed over 100 patent families. So our group, between Australia and New Zealand, our group is regarded as one of the most commercially successful research units, because all those patents that we have developed, they're commercialized, and things that you use daily, like your cell phone, charging, your monitors on your TV screen, they're actually being built using technology that we commercialized into the world 30 years ago, 20 years ago, 10 years ago. So some of the technologies that we developed in that research unit, they're already in your lives, regardless where in the world you are. And as a result, we are regarded very well in the power electronics area. So that's a bit of an introduction to our university, the research group I come from. I consider myself as the 3rd generation. I was a student of Professor Uday Madhavela, who was a student of Professor John Boyce. So I'm like the 3rd in the sort of history of our research group. Professor John Boyce is quite old now. He's retired. The group is now led by Professor Grant Kovic. We work together quite closely. And then we got Professor Patrick, who all four of us together, we sort of look after about 35 PhD students and about 10 plus postdoctoral students. Right, so let's go into the wireless power area, see what is around, what is first wireless power, and what's been the history of wireless power. Right, so before we sort of go into the technology, if we take a step back and look at wireless power, we could divide that into two broad categories. One is long distance transmission, so transmitting from here, maybe a kilometer away. That we call the radiative transmission technology. And the other sort of broad category is short distance transmission, transmitting from here, maybe 100 millimeters, 200 millimeters, about a meter. That we call closed range transmission using near field technologies. Long range transmission, people have done it for years, but it's still at an experimental stage because it's really hard to beam energy across multiple kilometers away efficiently. So you can see some photos here. In the 1970s, NASA has transmitted power over 1.5 kilometers, tens of kilowatts at good efficiencies. But the problem is if someone goes through that beam, there's health effects, there's regulatory effects in terms of health and safety. A similar experiment has been done in Japan recently. You could see there's a photo down there, long range transmission. So because of these restrictions around long range transmission, it's still at an early stage of research. You wouldn't find commercial uses of this technology yet, but there's quite a bit of interest. For example, transmitting energy from the space down to Earth, or transmitting energy in very sort of between cities, or to drones. Technologies that are used, radio waves is one of the ways to transmit long-range energy, but also people are looking at ultrasound, and also light. So you're beaming infrared over long distances. But like I said, nevertheless, it's still at a very early research stage. However, non-radiative transmission using near-field principles, it's been around for many, many years. It's been used in industrial applications for many years. And in the near-field transmission, we got two competing technologies. One is inductive power transfer. The other is capacitive power transfer. So inductive power transfer transfers energy short distance using magnetic induction. Capacitive power transfer transmits energy short distance using electric fields. The two differences. Capacitive power transfer is a little bit in early stages still. There's not too many applications of it because inductive power transfer tends to be much more easier to develop, much more efficient to develop. So as a result, most of the commercial development has been around inductive power transfer. So let's look at the history a little bit. So wireless power transfer, nowadays there's a lot of talk about wireless power transfer, but it's not new. It started in the 80s. Tesla, some of you might have heard, Tesla did some of the original work around wireless power transfer. It was followed by two people, LeBlanc and Hooding. They basically took Tesla's learnings and converted that into more real-life practical engineering. After sort of that 1880s to 1920s development that was done around wireless power transfer, there was a bit of a time period there was nothing happening. Then in the 1960s, a US researcher called Shooter started working on wireless power transfer for biomedical applications because there was a big boom around biomedical engineering. We had to get energy inside the body, wires were not good, and they started looking at wireless power transfer. He did a lot of work that are even to date used as some of the fundamental principles. He did kilowatts of power. He did use modern technologies like lead wire, semiconductors, and so on. So after the 1960s, most of the wireless power developments happened at the University of Auckland. And that's why we are quite famous for wireless power transfer. So Shooter did some work in the US, and after that, one of our professors, Professor Otto, he started conceptualizing how wireless power transfer might be used in electric vehicles and how it could be used in industrial applications. That work was picked up by Professor John Boyce in the 80s after Professor Don Otto passed away. And he developed that together with his industry contacts into industrial applications. And he was helped with Professor Grant Kovic and Dr. Green, and they sort of started working with industry. So you can see some of the photos underneath. And the last photo, which is a circuit diagram, is the first circuit that the University of Auckland developed using modern day semiconductor technology to allow wireless power transfer in an industrial scale. All the work before that, that was done by Tesla, Hooting, Shooter, they were at more of an experimental stage. Then after 2000s, we commercialized the technology with companies like Wampler, Daifuku, and that was out there in industry, in clean factories, in automotive manufacturers, factory floors. They were using inductive power transfer in the 1990s. That was developed at the University of Auckland. And people around the world saw that, okay, now this is a viable technology. We can use it in other areas. In the 2000s, everyone was thinking, okay, wireless power transfer is a great way to do electric vehicle charging, consumer electronics, and so on. So there was a big boom in the 2000s. You can see a lot of people, a lot of universities around the world starting wireless power transfer and also commercializing it. Underneath, there's a little photo. I don't know that you can read it, but it shows the timeline from the University of Auckland's sort of development, where we started developing wireless power transfer solutions for industrial applications, clean rooms, automation, then going into consumer electronics, electric bus charging, and then finally now going into the electric vehicle charging. And throughout, we've been working together with industry, commercializing our ideas. So you can see originally we worked with a company called Daifuku, then Wampler. So Daifuku is a Japanese company, Wampler is a German company. And then we worked with 3i Innovations for road lighting. Then we worked with Power by Proxy, which is now Apple. So Apple, everyone knows about Apple. We worked with them building wireless charging for phones. And then we went into electric vehicle charging with companies like Qualcomm, White-City, and now we are working with even the aviation industry with companies like Airbus, going and taking this wireless power transfer technology, helping them decarbonize aviation, electric transportation. Right, so that's the inductive power transfer side of the story. In terms of the long range transmission, like I said, it's still at an early stage. There are companies, startups looking at technologies like infrared beaming, RF technologies, RF beaming, and also capacity power transfer for very specialized applications. However, they're still at very early stages. It's not as popular or industrially used or used in consumer products yet. To summarize, IPD technology is regarded currently the most commercially successful technology when it comes to wireless power transfer. We could achieve efficiencies over 97%. So it's as efficient as you plugging in something onto the wall. And you don't have the hassle because there's no wires, there's no connection, there's nothing to wear off. We could transfer energy efficiently up to about a half a meter quite reliably. We could allow tolerances, so you don't have to be perfectly aligned. You can be driving in a car to get wirelessly charged, and as long as you park within the two strips, you would get charged. And we can transfer power efficiently and safely as well, making sure that people around the car would not have any health effects because of it. All right, so how do we do this is the next part of the presentation. What is wireless power transfer technology and what is the fundamentals behind wireless power transfer technology? Anyone here heard about wireless power transfer before? No? Okay, so let's start looking at some of the basics. Right, so a wireless power transfer system, we can divide into multiple. So this section has a little bit of maths and a little bit of circuit diagrams. Apologies early on. So what we do is we have energy source coming from, let's say, your plug point or a renewable energy system like a solar panel on your roof, some energy source or a battery, right? Energy comes in, it's usually rectified into DC if it's AC, low frequency. If it's DC, then you take the DC. Then what we do is we had to turn that energy into very high frequency, because the efficiency of the wireless power transfer and the size of the wireless power transfer system, you can reduce the size, improve the efficiency by increasing the frequency of the energy that you transmit. So what we do is we have this thing called a power electronic circuit that takes the energy in the form of DC, converts it to high frequency AC. And then we pass it through a series of networks. The energy transfer, because it's inductive power transfer, happens between two coils. You have a transmitter coil and a receiver coil. The transmitter coil emits a magnetic field, which the receiver coil receives and extracts energy of to supply wireless energy to the secondary. So the key part of a wireless power transfer system is the coil, the two coils, the transmitter coil and the receiver coil. And that essentially sets the efficiency and the operational properties of the system. So looking at the transmitter coil, how many electrical students are here? Studying electronics, electrical? Some of you? So if you're an electrical student, you know about transformers. And a wireless power transfer system, we can think of it as a transformer, but a very bad transformer. If you put 10 amps into the primary, because your magnetic field is not very well coupled to the secondary, maybe you might extract 1 amp out of it, if you're lucky. So the coupling between your transmitting coil, so the energy coupling between the transmitting coil and the receiving coil is quite low. For a traditional transformer, it's in the 99 point something%. For a wireless power transfer system, it's less than 40%, most likely 10-20%. Okay? So you put 100% energy, you only couple 10% energy. How do we make it still operate at 97% efficiency? This is the question we are trying to answer. Now we can model the wireless power transfer system as a transformer, but as a wireless power transfer engineer, we don't use that model. We just show it to show that it's similar to a transformer, but a very bad transformer. What we do is we model it as what we called two coils that are magnetically coupled. If you put a current into one coil, like Faraday said, it induces a voltage on the secondary coil. Okay? Now, you put a current, you induce a voltage. And Faraday said that higher the frequency, the more voltage you induce on the secondary coil, right? And Ampere said that if you had more current in the primary coil, you get more voltage on the secondary coil. So basically, we use Faraday's principles and Ampere's principles, and we can explain how wireless power transfer system works. So you put more current into the primary coil, you get more voltage on the secondary. You put more frequency in the system, higher voltage. Now, taking that, how do we actually think about the power transfer happening between the transmitting coil and the receiving coil? We can extend this. If you're good with mathematics and complex numbers, you know the voltage, you know the current. Power is voltage times current, right? So you can multiply them together. Of course, there's reactive elements, so you have to multiply it in the complex domain, right? And then you get an expression for the wireless, the power transfer from the transmitting coil to the receiving coil as a function of how good the coupling is between them and how much energy you put into each of those coils. And it's simply, no matter how many fancy things you have in your design, it's simply the coupling factor times the amount of volt amps in your primary coil and the secondary coil, square root of that. So it's a very simple relationship. And sine theta in that equation normally is 1. So if you want more power, you put more volt amps into the two coils or improve the coupling between the two coils. Like I said, for a typical inductive power transfer system, coupling is in the 10 to 20, maybe 30% if you're lucky. 40% is a quite luxury, I would say. Now, if you want to extend that analysis a little bit, you could model the losses in the coils, because when you have current going through coils, you have losses in the coil because coils have some resistance, right? So that resistance dissipates energy, and you can find a theoretical efficiency for a wireless power transfer system. And you can use your differentiation, find the maximum of that, and figure out when is the maximum efficiency of a wireless power transfer system happens. Now, I wouldn't bore you with that. If we sort of go to the next slide, what we are doing here is using that relationship, showing that for a typical system, if you have good coupling, we could get good efficiencies, 97, 98, 95% efficiencies. And that's because although 100% of the energy is not coupled, as long as you have efficient systems, efficient coil design, efficient power electronics, we can circulate the energy back to the source. However, as soon as your coupling starts decreasing, maybe below 10%, then the efficiency would start dipping down. So we want the coupling to be good, but doesn't need to be very good. Okay, so that's how the energy transfer happens between the primary and the secondary, or the transmitting and the receiving coils of an inductive power transfer system. How do these coils look like in real life is the next question. Okay, let's have a quick look. Traditionally, there have been two major options for these transmitting and receiving coils. One is an elongated track. If we have a system in a factory, like in a clean room or an automotive factory where you have a production line, you're transmitting wireless power, it needs to be a long track. But if you want higher efficiency, we tend to do what we called lumped coils. So you can see first picture on the top is a track. The second picture is what we called a circular coil or a circular transmitting coil. It's just a number of turns wound as a circular coil. The next one is a little bit more of a complicated coil structure, which we called multi-coil systems. And then last one is a little bit more even fancier, which we called ferrite-less systems. Let's have a look at a little bit of a closer look at the simple structure, which is the circular coil. In that coil, what we have is a copper winding that forms that coil, and under the copper winding, we have a magnetic material, a permeable material, magnetically permeable material, something like ferrite that is good at high frequencies. And the reason we have this is, with the help of that magnetic material, we can direct the magnetic flux onto one side where we want to transmit the energy. So you have the ferrite, which is the blocks that are shown in the diagram, and then the coil, which is the yellow part, and that creates a magnetic field to shoot up from the center and come back onto the sides. Okay? And if you put another coil on the top, the magnetic field would basically go from the center to the other coil center and then come back from the sides, return it. Completing that Ampere-Faraday relationship, inducing a voltage on the secondary. So this we called non-polarized coils, or simply circular coil. If you want to make it a little bit better, if you want to specifically improve that coupling, K, then we can explore new options. One of the things that our university is famous for is this called the double D coil design. And this one is two coils together, and now it's a north and a south pole on each coil. So instead of in a circular coil, flux magnetic field starts from the middle, comes to the edge. This one, magnetic field starts from one side and goes to the other side, which improves the coupling, energy coupling between the primary and the secondary. Then we looked at how do we improve even further. We have patents around multi-coil structures. So adding more coils that might have different current phases, providing even better performance. So all that we are doing to improve that coupling factor, or the energy coupling from the transmitting coil to the receiving coil, because that's directly proportional to how much power we can get from the primary to the secondary. The next line of work we do is how do we make it efficient? Now, when you have a coil, you want to put tens of amps into it at high frequencies. It's a lot of voltage and current, right? Because you have a coil at a high frequency, it has a certain reactance. Reactance times the current is the voltage. Both voltage and the current is quite high. So how do we do it more efficiently? And how do we extract energy more efficiently from the secondary or the receiver? The biggest problem is we have a voltage source, but in series with that voltage source, there's an inductor. Inductor stops energy going into our resistor, which is our load. So we want to get rid of that inductor. And that's where we use some of the principles that were developed by very early researchers like Hertz. Hertz said that if you go and put in a capacitor in series with that inductor, they will start resonating. Inductors have positive reactances, capacitors have negative reactances. And at the resonant frequency, the two would be equal. Positive plus a negative becomes zero. So what we can do is we can take this, which limits the energy transfer. We can convert it into an ideal voltage source by putting in a capacitor in series. Or we can put a capacitor in parallel to convert it into a current source. So we take this system that had high voltages and high currents, put a compensation capacitor either in series or parallel, converting it to an ideal voltage or a current source, allowing us to get any amount of power into the secondary, although the energy coupling is less than 40%. And you can do the same thing on the primary side. The primary side, the power electronics needs to generate that voltage and the current, and it's helped by putting this compensation. Okay. So that's how, in essence, a wireless power transfer system works. You've got two coils, a transmitter coil, a receiver coil, and we try to design these coils as best as possible so you improve the coupling. And then we try to do compensation of the coils using capacitors, or we can do more complicated things, capacitors and inductors, to improve the efficiency by reducing the VA, or the voltage and current we need from the power electronics, because the power electronics can be inefficient. Now, in that sort of respect, what have we done in terms of research at the University of Auckland? So this is our team. You can see it's a lot of people. It's not just myself, or it's not just Professor Grant Kovic. We got a very multidisciplinary team. We got people from the electrical area. We got people from the mechanical area. We got people from the civil. We got people from the business school. We got people from material science. So we have a very wide team. And we have projects that are funded both by the government and the industry that's looking at all sort of aspects of wireless power transfer, with the focus of helping decarbonize transportation. So we don't work just ourselves in the University of Auckland. You can see we work with local, other universities, as well as international universities like University of Cambridge or Utah State University in the US. We work with industry, Vitrocity, Airbus, and so on. So it's a large team of researchers working and developing solutions to help decarbonize. Now, what are our capabilities? Because we got such a wide range of expertise, we can do a lot of things that most other research teams can't do. We have experts who can design power electronics, new power converters, new compensation techniques, optimize them. We got experts who can design transmit and receiver coils, new designs, patentable technologies, optimizing it. We got scientists that helps us write algorithms, machine learning algorithms, genetic algorithms that helps us optimize these coil designs to get the best out of it. Then we got mechanical engineers who help us with the thermal and the structural modeling to make sure they are reliably going to operate both thermally and structurally. Then we have civil engineers and economic people, business school, helping us looking at the econometrics, the use in roads. How do we model? We have simulators that simulate if we bury these transmitting coils in a road, how long would they survive when heavy vehicles are running over them? So we have a huge team of people looking at all aspects of this research. So in terms of my students, PhD students, so although we are a large team, each of us academics have our own PhD students looking at a smaller part of it. Some of the work my students have done, we've done things like active rectification to help improve efficiency, as well as if you have seen some of the products with phones, they call it two-way power transfer. So you can use your power bank to charge the phone and then also phone to charge your earbuds. That's some technology that we developed in our group. We are also working with much more complicated compensation techniques. So two ways to control power. One is using power electronics, and the other method is having intelligently, passively adapting compensation networks. So we developed a number of compensation technologies that are now being adapted by other institutes and improved on, which we call the hybrid compensation techniques. Then we look at new power converters. Traditionally, power electronics, if you have learned about power electronics, we talk about full bridges, half bridges, and so on, but they have limitations. So at Auckland University, we developed this new sort of converters, which we call the boost active bridges or modular boost active bridges. So with using these new technologies, we can further improve the efficiency of wireless power transfer. We got right now a system in the lab. I was in a meeting with some of my students in the lab. We are transferring 80 kilowatts wirelessly at an efficiency of 98%. So it's as good as you can plug in into a vehicle. So you can see some of the efficiency plots here, quite efficient and very flat efficiency curves. We are looking at how do we scale up into, everyone wants to charge vehicles fast. You don't want to be staying in a charging station for an hour or half an hour. You want it to be charged in 15 minutes. So we are looking at how do we improve the power capability. So we're looking at things like multi-level converters and how could we use multi-level converters to use cheaper devices to build a cheaper system, but a higher power system. And while we're doing it, we're also looking at, can we use intelligent control techniques to improve the efficiency further? So this system, with traditional control, we are getting in the range of 93, 92% efficiency. But with new control, we can improve that much further into 95, 96%. So not just the power converters, but we're also looking at control techniques. And that's sort of together with both the control, the power electronics, the compensation, combining all that expertise, we can develop much more elegant systems that are cheap, but also very efficient to operate in. Now, another piece of work we do is how do we sort of reduce the cost further? Because one of the other things that we want to do is to reduce the size of the battery in the car. Batteries are expensive, make the car more expensive, electric vehicle more expensive. So if you want to reduce the battery, we want the car to be regularly charged. So one of the things we are looking at is, can we have electric roadways? So you have wireless transmitters under your road. When you drive on the road, it gets charged as you go. And that way you can reduce the amount of batteries you want. But to put so many of kilometers of electric roadways, you need to have cheap solutions. So we are looking at how do we reduce the cost even further. So this is one of the pieces of work we started with, and then it sort of progressed into a system that allows you to have multiple modules along the road where you only have one power electronic switch to control each module. And as the vehicle comes on, it energizes, charges, and then it moves on to the next transmitter, charges, and as we go a few kilometers, you might get enough energy so that you don't have to have a large battery in your car. And you don't have to go and charge every 100 kilometers or 200 kilometers. Now, the final piece of work I'll show you is to do all that, we need to know and understand the efficiency of the system. And some of the challenging things about wireless power trans systems is it's operating at high frequencies, high currents, high voltages, also quite large, high temperatures. Modeling losses is very hard. So we are developing techniques, not just the electronics, the compensation, the control, but also techniques to measure things accurately so that we can go and develop computer models that tells us a big picture, what we call is a coupled multi-physics model. So we don't have to go and build everything. If we have a good model, then we can simulate the electrical side, we can simulate the mechanical side, we can simulate the thermal side, the magnetics, everything can be simulated and further optimized. So we are working on measurement techniques that will help us develop this high fidelity models in simulation. So that's the end of my presentation. I made sure I had 10 minutes for questions, so went through it a little bit fast. Yeah, we can now take questions.
Okay, we open the floor for question and answer session. So if you have any question regarding the power transfer that you might like to know further, you can ask me, Dr. Duleepa. Tak ada. Nanti nak tanya. Nak tanya soalan Dr. ni. Okay. So I guess that is all, Dr. Duleepa. No question. It looks like everybody understand.
Yeah.
Okay.
It seems so.
Okay. We are actually honored to have Dr. Duleepa J. Thrimawithana sharing his expertise on the energy sector. Okay, his valuable insight have broadened our understanding, and we extend our gratitude to Dr. Thrimawithana and all the participants for contributing to the success of this keynote event. Let us give him another warm round of applause for his remarkable keynote address. before we end this session, I would like to call upon our rector, Professor Dr. T.S. Mazida Puteh, to present a gift to Dr. Duleepa as our token of appreciation. Okay, thank you, Dr. Duleepa. Thank you, Prof. Mazida. Okay, and that's remark at the end of our keynote session. Again, I would like to thank all the participants. Okay, and then we hope to see Dr. Duleepa again. Please come again later. Okay, thank you very much. And tak ada dah. Okay, thank you. Next will be the parallel session. So students are free to go to their respective parallel session. Yeah?